All right, why don't we get started? So, where we left off last time, we talked about the correspondence problem and we discussed the trade-offs from an engineering standpoint concerned with the correspondence problem. And so, for correspondence, you have some notion of a query, and that query is some patch of image or object in one version of an image that you want to find for which you want to find where it moved in the next image. And so the setup is either you have one camera that moves or you have two cameras. Nonetheless, you have two images, T0 and T1. And in this example, we have the cropped pink region of the image at time T0, and we want to find where it went at time T1, where it went in the image, in image coordinates. And so you start out, you initialize your search, and here you can see at the version of the image for time T1, we have this dotted version of a cropped region. And so we're going to take that dotted search, if you will, search area, and we're going to move that around the image in regular increments, looking for that part of the image at time T1 that most closely matches the original position of that particular patch in the image at time T0. And so you start out, you initialize your search, you have your query, and that query remains fixed. And then you have the cropped region in that image at time T1 in its first position. You compute some score like correlation. It gives you a value where that value will range, in this case, from 0 to +1. Certainly correlation itself as a measurement can range from -1 to +1, but you tend to get minus negative values if you're dealing with negatives at time T1. And that's not the case here. So we compute that score, and then we maintain our query in the next round, and we move our search window, update our search, and compute that correlation again. Right? And so we do that over and over and over and over, maintaining that correlation value that is maximum, and that's going to be our match candidate. Okay, so as an algorithm, you initialize the query, step one. Step two, you're going to loop. Step three, you're going to continually crop. You're going to make a comparison, save the match score, and then update that search location. And at the end of it all, that location corresponding to the highest match score, in this case we're using correlation as the match score, will be the new location of that original patch from the image at time T0 when it moved to some position at time T1. Okay. Any questions about this? So then the trade-off is between granularity and resolution. At one extreme, we could take our image at T1 and we can tessellate it. We kind of chop it up into non-overlapping regions, and then we search each region or treat each region as a search area in the image at time T1. Now, certainly, this is very fast because you're spanning that image in a very relatively smaller number of search regions. But this does not give you very high level of granularity. And so if your match or best match doesn't align perfectly with one of these search regions in the tessellated version of T1, you're not going to get the precise location where that patch moved from time T0 to time T1. On the flip side, you could, instead of tessellating the image at T1, you could slide that search window one pixel at a time. Right? That's the smallest way you can update your search region at T1. And if you do that, absolutely, you will get very fine-grained resolution, meaning that you can capture where that object depicted in the search region, where it moved precisely. But the problem is you have a lot of pixel locations that you can position the search window in, and that's going to result in taking a very long time to do this search. Okay, so there's a trade-off, and which is right? Well, it depends on your application. At one extreme, you have fast search, but very low level of granularity. On the other extreme, you have high level of granularity, high resolution in your search, but you have your execution time takes a lot longer. Okay, all right. Any questions about this? All right. You can also use some constraints to help you out. Now, if you have a moving camera, if you know how fast the camera is moving, Well, based on the motion of the camera, the objects depicted in the image returned by the camera cannot have moved more than a certain distance or delta plus minus in every direction, north, south, east, west, when it arrived upon a new location at time t1. And so knowing the constraint about how motion works, you can limit that search window to some region around the last known location in the image when you last saw it at time t0. Right? So in that case, instead of searching the entire image t1, you're only going to search this blue region as depicted in the image at time t1, which is just the original location plus or minus some delta in all directions. Okay. Any questions about this? No? All right. So let's try this in MATLAB, and that's where we left off last time. And I'm going to do this whole example in MATLAB and show you the trade-offs, go over the code. And then after this, open it up for questions as far as the exam on Thursday is concerned. Okay. So let me bring up MATLAB. And I'm going to bring up Correspondence Finder, and I'll post this after class, the source code, so that you can tinker with it yourself. So we have two different images. One I call Oprah Head, and Oprah Head has been cropped out of another image of Oprah in a crowd or among a group of people. And so the smaller image here in the upper left, that's Oprah Head, right? And the larger image is the original image. They're at some Broadway show or something like that, or some stage performance. And so what I'm going to do is use correlation as the matching score to actually find the location in this Oprah in a crowd image. Where is Oprah's headshot located within the image? Now, certainly, of course, you can see it. It's right there. And to make the problem a little bit easier, I'm using the same set of pixels for the headshot as is what's inside of the image itself. But this will work with a different image of Oprah for headshot, provided that many of the features are the same. Maybe the lighting is the same, the glasses are similar, but not necessarily the same. But you'll find this gets less and less accurate as the headshot changes. So, if she's facing the camera or the camera is in front of Oprah's face when it takes the picture for the headshot, then it should match fairly well, given relative same lighting and glasses and stuff like that. But if she's turned 45 degrees and you get that semi-profile view, then it's going to be a little bit harder to find a precise match. But nonetheless, we have what should be an exact match in the headshot, and then we have the image from which that came of Oprah in a crowd. Okay, so we start out, and let me blow this up a little bit, enlarge this. And we have the query image name, that's Oprah Head, and we have Oprah in a crowd, which is the other image. So you can imagine that image patch that we alluded to before from the slides from class. That would be corresponding to our Oprah Head. That's the cropped region, pink region. And we're going to try different locations within this second image in a crowd and show you how those trade-offs look in real terms. And so I have a variable here, and that's called show crop search. And what I'm going to do is actually show you what is being searched within the larger image, what set of pixels, what patch or region of the image is being searched when we do the comparison. And so I start out, and I read the images, and I convert them to grayscale. Now, certainly, you don't have to do it in grayscale. Grayscale makes it a little easier, but if color is really important to the description of all the objects in your image, you'd certainly want to use color. And how you use color is the subject of our next module that we'll talk about after the exam on Thursday. Okay, so we start out, we read in both images, and you can see one of the images, the original image in a crowd, that's 631 rows by 640 columns. And then the query image, which is the smaller headshot, it's 178 by 119. And of course, going back to what we talked about when we discussed RGB or red, green, blue representation, you notice this third dimension here for the original image is 3, right? The first represents the red component, second represents the green component, and the third represents the blue component. And as we saw, there are different slices, if you will, in like a 3-layer matrix, if you will. And if we look at the query, the original query, that third dimension is 3 pixels wide for the R, G, and B components. And when we convert to grayscale, you notice it's just a 2-dimensional matrix, and we no longer have that third dimension because we're effectively replacing the red, green, blue with a single value between 0 and 255, where that number is calculated by this RGB to gray by taking equal components, 0.33 times the red component, the green component, and the blue component. Okay. Any questions about this? Does that make sense? Yeah? All right. So we take a few measurements of both the query image and the query rows, okay, and then we define here on line 43 something I'm going to call the X shift and the Y shift. So I'm going to start out setting those both to 1, and what X shift and Y shift are going to control is the number of pixels the search window moves in the X direction to the right and in the Y direction down as we update the search window. So we're going to start in the upper left-hand corner of the query image, right? That's that bigger image of Oprah in a crowd. We're going to crop out a patch of that image, do a comparison, and then we're going to update the search region. And we're going to do that by adding to X shift and adding to Y shift. In this case, I set them both to 1, and so we're going to just move it to the left, to the right, 1 pixel at a time. And then once we get to the end of the image with that crop search window, we're going to go to the next row, and that's where the Y shift comes into play. Okay. Any questions? Does that make sense? Yeah. Okay. So now this next array position, that's going to be something used to describe both the X and Y position, the width and the height of that crop rectangle, right? So that's going to define for us a rectangle. And that rectangle is going to be the location and the description, width, and height of that region of image, that rectangular region of image that we're going to crop out or make a copy of when we're going to compare the original headshot to that location to some location in the query image, right? And so this is typical of MATLAB when you're drawing shapes. We have X, Y, the first 2 positions in this 4 array. Are going to be the X and the Y location, and that's in image coordinates. And then we're going to have next 2 numbers, width and height. That's the width, so along the X direction, and the height along the Y direction of that rectangle. And so typically when you define rectangles, you define the corner point along with the width and the height. Okay. Any questions? No? All right. So now we're going to initialize a couple variables that we're going to use to track both the location in terms of the X and Y corner point for the rectangle, as well as the correlation score, the maximum correlation score. And so we initialize those to negative numbers to make it what's called fail stop, right? Oftentimes, and this is just more of a software engineering thing, when you initialize variables, you can have a particularly damning feature called a Byzantine failure. And what a Byzantine failure is one where your program has failed, but it's still running and producing values, right? Now, because it's still running and producing values, it makes it particularly hard to debug. So when you initialize your variables, choose variables that are values that will cause your program to break, right? And so by choosing negative values in MATLAB, because you can't have negative 1,000 as a correlation score, and you can't have a negative number as an XY location in an image, this will cause the program to break should it start running without ever updating, right? And so that's called fail stop. You want to initialize the initial state of your variables so that your program will break, because if it breaks, it's a lot easier to debug, and you'll notice very quickly that, oh, I initialize it, but I'm never using updating these variables. And so I initialize the max correlation score, and that's going to be large negative value, and that's going to hold the correlation associated with the best match for some location in the query image between some location in the query image and that's some location in the search image and that query image, namely the headshot. And so I save not only the maximum correlation score, I also save the corner point x and y in image coordinates associated with the best match in that larger image. Okay, so I do some initialization. The current correlation score, I set that to whatever the max is, and then I iterate through my larger image. So I have my x and y values, and so you'll notice here I'm going what's called row major, right? I start out y is one value, and then I change x. So I'm going to go across the image. It doesn't matter if you go down or if you go across. It just looks better to me if you go across. And so I have y is initialized to 1, x is initialized to 1, and I'm going to increment by an amount equal to x shift and y shift respectively. Now, again, as I said before, x shift and y shift controls how much you move that search window every time you update where you're going to crop within that larger image trying to find the headshot. Okay, and so I shift by a y shift and x shift respectively for my y and x values and image coordinates, and then I only go up to the number of rows minus the crop rows and the number of columns minus the crop columns. Now what that is for, when I describe the crop window that I'm going to use to take pixels from that larger image to do the comparison using correlation, I don't want that x and y describes the upper left hand corner of that crop rectangle. And so I don't want that rectangle to be such that part of that rectangle is outside of the defined pixels of the image, right? And so I'm going to stop at image rows minus crop rows because I want that right-hand edge of the crop rectangle to align with the right-hand edge of the image, and then I go to the next row. Okay, so that's to prevent my cropping rectangle from falling off the edge, as it were, of that image in which I'm searching for potential best matches. Okay, any questions about this? No? All right. So here I have my crop, right? That's IamCrop. That's a MATLAB API call. And when you crop, you give it the image from which you want to crop pixels. So to crop means to cut out or to make a copy of. And I'm making a copy of pixels in that larger image, and it's going to be a rectangular crop. And so I give it image I, and then I give it an array with 4 different values, the x and the y, so the location of the upper left-hand corner of that crop rectangle, and then how many columns and how many rows for the width and the height of that crop rectangle. Now, certainly when you do a crop, right, the values you give it for the width and height are always 1 less than the number of pixels it gives you, right? It's a little bit confusing, but if you read the API, it'll just tell you, and you just try a few times the values, look at the size of the cropped out region, and then adjust accordingly. So this call to IamCrop says go ahead and make a copy of a rectangle at a certain position with a certain width and height out of that image I, where the image I is that larger image that depicts Oprah among a bunch of people in the theater. Okay, so now I compute Grayscale, a version of that cropped image, because when I crop, I'm cropping from the RGB image, right? I don't make that assumption that the image is not RGB. And then I make sure that my query is also RGB. It is, I'm sorry, it's already grayscale. It is grayscale from before, but I just like to put that in as a safety check. And then inside of this if block, that's a little bit of bookkeeping just to plot some things. And I plot 4 things. I plot the query image, which is the headshot. I plot the crop region, which is the rectangular region of the larger image that I've copied. And then I also plot what's called the continuous histogram. And so this continuous histogram, is going to show you the red, green, and blue components in a very compact way. And so it's going to have a graph. And that graph, just like any histogram, the horizontal axis will represent the saturation of red or saturation of green, saturation of blue, and the vertical axis will represent the counts. But in this case, it's going to have 3 graphs. One's going to be colored in red, one's going to be colored in green, one's going to be colored in blue to represent the red, green, and blue component. And so I show the histogram for color histogram of both the query image, which remains fixed because it doesn't change, and the cropped image, which will change because I'm updating the crop rectangle to take out and copy different regions of that larger image. Right. And so that's just to show you from a visualization perspective that as you change the crop region, so too does the set of pixels and their colors change, and just to show you how it's updating. Okay, so then I also show the original image, and then I compute a rectangle in red to show you what that region is, where it's located in the larger image in which I'm searching. Okay. Um, so now after that, I compute the correlation score. Now this correlation score is inside my correlation match. And so I have two images. One image is the grayscale version of the cropped region, and one image is this grayscale version of the query image. And so I take those two and I compute correlation. How do I do that? So I start out and I take each image. Remember, an image is a two-dimensional array in grayscale, right? And so I do what's called flattening that image, right? I take each row of the image, I concatenate them together using this reshape API call in MATLAB. Excuse me. And the reason I do that is because I want a set of values as a single array over which I can compute something like correlation, right? To actually compute a statistic on all those pixel values from the grayscale image. And I wrap that reshaped grayscale, those reshaped grayscale images in a double because I'm going to calculate a value. I want to use double to do that because unsigned 8-bit integer is too small of precision to calculate any kind of values you might want to compute. So I do that, and I then compute correlation using the API called core in MATLAB, and that returns back rho, which is my correlation coefficient, and I return that from my function. So popping back out, I return that correlation score, and I compare the correlation score for the current cropped region from the larger image with whatever the maximum was, and then I update, and my loop iterates, and then when I'm left with is that max that I hang on to. I record its X and Y corner point for its position, and then I draw the rectangle in the position of the larger image where that best match is located. Okay, any questions about this? Does that make sense? All right. So let's try this out, and let me come down here and show you the first iteration, and then we'll just let it spin for a while and discuss these trade-offs that we had spoken about moments ago. All right, so let me run this. Okay, let me go past here, read the images. Where's my breakpoint? It's down here. All right, so continue. Okay, so let me get rid of this image view, and let me increase the size of these both. So here on the left, your left, I have the original image. And you'll notice here I have this red rectangle in the upper left-hand corner of the original image. And on the right-hand side, I have two things. I have the query image, which is the headshot, the Oprah headshot. And then I also have these two continuous histograms. So I have Oprah's headshot, and to the right of that is the continuous RGB histogram that describes the distribution of red pixels, which is this red curve, green pixels, which is the green curve, and blue pixels, which is the blue curve. Now, this histogram will not change because I'm not changing at all what the query image is. But what you will notice here, this other image in the second row, that is the content for the patch of image that's copied from the current location of the crop of the excuse me of the crop window. And what you'll see here to its right is the RGB histogram associated with the pixels for that cropped region. Let me adjust this. My glasses just got... Okay, and so to the right of it you'll see its continuous RGB histogram describing the distribution of red, green, and blue pixels components associated with that crop region. Okay, so X shift and Y shift at this juncture, they're both 1, right? And since they're both 1, when I update this region, you'll see this cropping rectangle move 1 pixel to the right. Okay, so let's try that. Let me say continue. So you see, well, it's maybe hard to see. Let me just let it run and let you see for yourself. Continue. So you'll see it doesn't move very quickly, and you'll see that the crop region, right, it changes ever so slightly, 1 pixel at a time. And you should see, let me see if I can bring this down here, that the histogram for the crop region, it doesn't change very much from one version to the next, right? Because if you think about it, if you move this crop region 1 pixel to the right, that left-hand slice, if you will, that left-hand column, that's the only set of pixels that change, right? And that's not a lot of pixels. And the result of that is that you see a very slight change in the resulting histogram on the bottom right-hand corner, right? So that's not very interesting, and you can see it's sort of trudging along very slowly, and I don't have time to actually let it go all the way to the end. But it's just to show you this is the minimum x shift, y shift, which is 1 pixel in x direction and 1 pixel in y direction. And of course, once it gets to the edge, the right-hand edge of the original image, it'll shift down to the next row, down 1 pixel, and continue, right? Okay, so let's stop that and let's change X shift and Y shift, and we'll see how that goes. So let's try X shift and Y shift is 64 pixels to the left and 64 pixels to the right, 64 pixels to the right and 64 pixels down, right? And so let's restart this and let's see, I cleared all the breakpoints. Let's see how this runs. And this should run fairly quickly. So if we do that, we'll notice it jumps more dramatically, right? And we see that the crop window, its histogram does change very dramatically. And you can actually see the pixels as they go, because if you jump 64 pixels to the right, it's going to be dramatically different. And so the end result is, well, it has part of Oprah's head, but it doesn't have the whole head. It's not really centered because we don't have the type of resolution we need in order to get a very good what's called localization or identification of the location of where those pixels moved, right? So let's try something a little bit less aggressive, right? So let's try something, in between 1 and 64. Let's say 32, right at the halfway point, and we'll see what happens. And so this is our location. It wasn't really centered well. It caught some of the pixels, many of them, but not all of them. So let's see what happens if we're halfway with respect to this X shift, Y shift of 32 pixels along X per shift and 32 pixels along Y per shift. So let's see what happens there. So you'll notice it's not jumping quite as dramatically. And while the pixels change in terms of the histogram for the distribution of the content, it's not jumping around as much as before in terms of one iteration to the next, right? And that's something called color constancy. If you go fewer number of pixels in an image, the pixels tend not to change as dramatically because color for objects tends to be relatively uniform, right? And so what you're seeing is that you see fewer changes in the histogram associated with the color content for the cropped region. Okay, and so certainly this is taking a little bit longer, or a bit longer than before when our X shift and our Y shift was 64. And so we'll let this one run to completion since it doesn't take horribly long, and we'll see what the match candidate was for this algorithm. And you should see that it's a little bit more accurate in terms of identifying the pixels for the headshot. And let's increase the size of this so we can see. And yeah, it does a pretty decent job. It's much more centered and identifies most of the pixels associated with Oprah's head, but it's a little bit off center slightly relative to the query image that we saw. And then lastly, if we were to do something like 12 or 10, you'll notice that it moves even more slowly. And we're not going to let this run to completion in the interest of time, but it moves even more slowly. And you will find that the histogram representing the content for the cropped region, it doesn't change quite as much as when it was 32, right? And if you let this run to completion, you'll see that the crop region is even more accurate in identifying where the headshot pixels moved within this particular image. Okay, so let me just 10, 3. Let me stop here if I can and take any questions. Any questions? Does that make sense? And so certainly, there's this trade-off, and what is the right trade-off to make? It depends on your application. And you'll see with applications like the 3D instant replay videos that I showed, typically for something at that scale, they're going to have custom hardware because you want things to be very, very fast. And as you can see, imagine if you're trying to find correspondences between two images and you want to do that very fast, you want to make sure you balance this trade-off correctly. On the new iPhones, I don't know as much about the Android products. If you go to your photos or you can take photographs, there's this setting for panorama, right? And you sit there with your camera and then you rotate in one direction and it takes all of those images and it so-called stitches them together. Essentially, what a panorama is doing is using correspondences, and then it's finding in one version of the image before you moved and after you moved what points correspond to one another. And once you find those correspondences, you can now align those pictures based on those correspondence points, and then you keep aligning them, aligning them, aligning them, and you get an entire panorama. Right? And that's exactly how that works. Now it works in real time because they have custom hardware on the iPhone hardware platform to speed that process up so that it happens in real time. But it's doing exactly the type of thing that we're talking about here, only it's burned out into custom hardware, especially because you want to get it to work fast in real time on a handheld platform. Okay? All right. Any questions about this? Does that make sense? Yeah. All right. Okay. So with that, let's uh, bring up the let's see list of topics for exam one, and everything that we've done this semester is fair game. And we've done, a fair amount of things. And what the purpose or goal of this exam is to bring together all that material similarly to what the homeworks do. And I would certainly ask you something related to the homeworks, but not in the same way as the homeworks, because when you're doing the homework, you have a lot more time in which to do it. And so we talked about a bunch of stuff over the different modules 1 through 8, right? We talked about measurements. We started and we motivated it with this idea or question: who's better, LeBron James or Michael Jordan? And we use that to motivate what is a statistic. Now, of course, it depends on what is important to you, right? And we use that discussion to motivate the idea of experimental design. What is it you're trying to measure? And anytime you see some statistic reported, it's important to understand what was measured and what you believe what those measurements mean. And so a statistic more generally is any function computed over the data. And we gave an example using the Gini index, and we used that to discuss the idea that for very many municipal concerns like governments, whether that's local, county, state, or federal, the outcome of these statistics is used to make policy decisions. And so we discussed at a high level different types of statistics. So-called descriptive statistics summarize something about the population under study. And so certain descriptive statistics like the mean, the median, percentiles, we went through a whole bunch of them. Um, so descriptive statistics summarize your things about your population. And then we talked about inference, right? And for this, we used the homeless population as our example, and we had a reinforcing homework. We had to go out and identify a population for survey design and report on that through some visualization. And so with this inference, the idea is that you have a population floating out there, and they're governed by some parameter, and you want to draw members of this population and compute a statistic over those members and hopefully be able to make a statement about the general population. And so that's called inference. And how you do inference is through sampling. We talked about risk assessment. We talked about the probability of bad things happening. And we spoke briefly about this idea of stock options, right? The more risky something is, you can protect that, but the more money you're going to pay associated with protecting against bad things happening. We talked about identification of relationships, and we had this sort of crime scene investigators type picture where they have the storyboard and they're drawing connections or evaluating relationships between various entities. We used a supply chain, the going from cacao to chocolate, and we discussed how different events at various related points can impact the end product. And so cacao is the plant or that is from which chocolate is derived. And if something happens at the plant side, maybe there's a pest or an insect that affects it, maybe inadequate rainfall affects it, the cost of chocolate at the end point is going to go up. And so understanding relationships between things and thinking about the strength of those relationships is really, really important. And that's one aspect of statistics that we talked about. Okay, visualization, we looked at different data types. You have ordinal variables, you have categorical variables, you have numeric variables that can be treated like categorical variables. Understanding the different data types and what they mean is really, really important. In the homework, when we talked about the zip codes and visualization, we had these different income level groups for each of the groups in each of the zip codes. Now, zip codes, they're numbers, but you can treat them like categories. And so you got a little bit of practice with that with the data types and also with charts, reading charts yourself. And, a geo-registered chart was that map application, but you also got some practice with charts for visualization of various sorts associated with the outcomes of your survey design. So we talked about sampling. We said that every population has these hidden parameters, ground truth floating out there, but you don't know what they are. And you should really think carefully about the population under consideration when you design an experiment. Doing so the right way leads to good results. The wrong way leads to bad results. And one example we gave is if you're doing a poll and you're only polling people using landlines, you're going to miss out on the demographic of relatively younger people who are cell phone only in their households. Okay. We talked about something called statistics and estimators, and the whole point of a statistic is to try to find some function that you can use its outcome as a replacement for that unknown ground truth parameter. And so these statistics are associated because they're over samples. Any errors that you make in sampling can affect the quality of the statistic. And so we talked about this idea of sampling errors, but then there's another type of non-sampling error. And a sampling error can be fixed, we discussed, by increasing the sample size, right? A non-sampling error deals with primarily a flaw with your experimental design. You have to do something differently. So increasing the number of people polled on a landline is not going to help your survey results if you want to know something about maybe some product usage, because doubling or tripling or having a 10x order of magnitude increase in landline surveys is not going to help identify people who are cell phone only. right? It's just not going to work. So you have to re-examine your protocol, how you carry out your survey design and your sampling if you want to fix so-called non-sampling errors. It's a structural issue with the design of your experiment. Okay, descriptive statistics, we've talked specifically about a number of them. We talked about the sample mean. We mentioned and had a homework on the sample variance. And these are estimators. And we talked about evaluation of the quality of an estimator. There were two of them, unbiased and consistency, where unbiased says that in expectation, the expectation of this estimator is exactly a particular parameter that is hidden from you, you don't have access to. We talked about unbiasedness. It talks about as you increase the sample size in the limit, so as n goes to infinity, that the probability that your estimator diverges from this unknown ground truth is going to go to 0, right? So these two together, if you find that an estimator is unbiased and consistent, then it is a good replacement for the unknown population parameter. And we showed this with the sample mean. We had a homework on this concerning the sample variance. And so we talked about the mean. We talked about the sample mean and the population version. We talked about the population median and the sample median as well. And of course, with that sample median, we looked at the case procedurally if there are an even number or an odd number, as well as an odd number of samples. We also talked about the relationship between the mean and the median and talked about whether or not a distribution is symmetric, left skewed, or right skewed. Now, that skewness talks about preference for certain values, right? Where the tails are located. Is the tail of the distribution to the right or to the left? And that's going to tell you that there's a preference, if you will, for certain types of values, the larger values or the smaller values. Okay. Percentile and quantile, we talked about those. Those are values, right? And those values have a relationship to other values, other samples that you've measured. And so this percentile talks about a value whose magnitude or value, or sample whose value is larger than a certain percentage of other measurements, right? That's your percentile. And then the quantile talks about those values, those points that partition your distribution into certain sized regions, right? So we talked about the quartiles, right? We talked about, the deciles, only very briefly, but there's a procedure for computing them that we mentioned. We talked about the sample variance and its relationships, and its relationship to the sample standard deviation. It is also a replacement that you can use for the population variance and population standard deviation. We also talked about measurements of dispersion and how you can use interquartile range and 1.5 times the interquartile range as a way of rejecting values or measuring dispersion of distributions. Okay. Visualization. We talked about histograms and the difference between a frequency and a relative frequency histogram, right? With the relative frequency histogram, you divide each bin count by the total number of samples, and it gives you exactly a distribution, right? We talked about mixtures and stem and leaf plot, which is sort of a back of the envelope type of histogram. So it'll be important to know which is the stem decimal place, which is the leaf decimal place. We talked about box plots, and using box plots is going to be very important. And it's a summary using the quartiles, the median, the mean, and looks at outliers as well. Image formation. We talked about peripheral and foveal vision. We talked about the pinhole camera, more introductory material, what the focal length is. We looked at eye trackers and talked about heat maps and discussed a few examples of usages and package design and product placement in stores for heat maps. We talked about correspondence, more generally, the finding of one patch of image in another version of the image. We looked at applications of correspondence, specifically the depth map, and mentioned how 3D instant replay arrives out of depth map. And so the depth map is using trigonometry to compute the distance from the camera of some object if you know the distance between the two cameras. We also talked a little bit about optic flow, more at a high level. And then we looked at RGB color space representation, intensity surface, that relief map treatment of an image in grayscale, and how you use a derivative and a convolution mask to encode the derivative, the partial derivative, in order to get so-called terrain features or the hilliness of the image as a way of describing the image's content. Um, we looked at this partial derivative. We developed the convolution mask from this partial derivative using the definition f of x plus delta x minus f of x over delta x in the limit as delta x goes to 0. We talked about how you use a tangent line to compute this, and you end up with a convolution mask, which is a 3 array that has values minus 1/2, 0, and plus 1/2. We showed an example of computing the edge map, and then we used percentiles in MATLAB example in class to show the top edges. And it was a city scene, and we extracted the vertical edges using the partial derivative along x, and showed how you can use percentiles to filter out weak edges to show you things like the windows and edges of buildings and things like that. Correspondence, we looked at searching in correspondence with that scene for the turrets, and we showed the query image and the target image, and we discussed the trade-off between granularity and speed. Okay. Any questions about this? Any specific questions about any of these topics? No questions? No. So you are allowed one 8.5, as is my practice, one 8.5 by 11 sheet of paper in the exam for your notes. I don't expect you to memorize stuff. What I'm looking for is an understanding of what the material means, right? So I'm not going to say, you know, what is correspondence? That's not the question I will ask, right? I'll ask a question of the sort that says, I'm using correspondence. Here's a source image. Here's a query image. This is what I got. What does this mean, right? So I'm asking conceptual understanding questions, and I don't expect you to memorize stuff. Hence, I allow you one 8.5 by 11 sheet of paper for your notes in the exam. Okay? All right. No questions? It's your chance. Questions on anything for this class? I can't tell you the meaning of life. Trying to figure that out myself too. But the no questions. So we've done a bunch of stuff, and it's all pulling together different data types, things that might be obvious data types, like things in table format, census data, IRS data, but also things that people typically don't think of as data types, like images and stuff like that. No questions? How many questions? That's a great question. Anywhere from 4 to 10. And what I do procedurally is I finish the questions, and I'm planning to finish them tonight, and then I take the exam myself, and then I multiply by 4 or 5, and I say how much will fit in about an hour. And so I don't really know ahead of time, but I always adjust it to give people about an hour to take the exam. And I usually spend about the first 10 minutes or so going over the questions in class to, if there's any ambiguity or confusion that people might have. And so to answer your question, I'm not sure, but anywhere from 4 to 10. And I always adjust based on what I think or believe that students can do in an hour. Okay. Any other questions? No? All right. So if there are no other questions, I'll end here. I didn't want to pollute things by covering a new topic. And so the slides are already posted for the next topic continuing on, but I'll end here, and I'll see you all on Thursday. Please make sure you get a good night's sleep and you study. Okay? All right.